In this course, we will be using a Python library specifically designed for machine learning called Scikit-Learn to learn about different supervised and unsupervised methods and their different application on real data. Scikit-Learn has a very resourceful and useful website that you can utilize to learn about different algorithms that this library has and even access to different examples and even data. So Scikit-Learn is a Python library that it's built on IPython, and it's compatible with other libraries of Python such as NumPy and SciPy and Matplotlib, which makes it perfect for a Python programmer. Scikit-Learn is very simple and efficient to use, and it's open source, so it's free. And it has all the algorithms for supervised learning, such as classification and regression, and also for unsupervised learning, such as clustering, dimensionality reduction, and also for model selection and pre-processing in different steps of machine learning when you want to build a model. A little bit about the history and background of Scikit-Learn. Scikit-Learn, interestingly, was initially developed by a guy named David Cornapio as a Google Summer of Code project in 2007. Later, Matthew Brocher joined the project and started to use the Scikit-Learn, the library, as a part of his thesis. In 2010, the INRIA, which is the French Institute for Science and Technology, got involved with the project, and the first release of the library, the version 0.1, was published later in January 2010. At the time of developing this slide, the project has more than 30 active contributors. Scikit-Learn provides a range of different machine learning algorithms, including supervised and unsupervised, via a consistent interface in Python. It is licensed under the Permissive Simplified Berkeley Software Distribution (BSD), and it is free. The Scikit-Learn library is built on the scientific Python SciPy that must be installed before you can use Scikit-Learn. Other libraries that are used in Scikit-Learn are NumPy, SciPy, Matplotlib, IPython, and SymPy. But if you actually install Anaconda, these libraries are already installed, and it makes your life so much easier. So to summarize, generally these would be the usual required library that we're gonna use when we want to develop or apply machine learning algorithms. The first one is NumPy, which is based on an n-dimensional array package. SciPy, fundamental library for scientific computing. Matplotlib, which is used for two-dimensional and three-dimensional plotting. Seaborn is another example. IPython, which is enhanced interactive console for programming using Python. SymPy, which is symbolic mathematics. And Pandas, which is a data-based library, data manipulation and analysis library in Python. Scikit-Learn is mainly for modeling and not data manipulation. For the data manipulation, we usually use other libraries such as NumPy and Pandas. Some popular methods, group of methods and tools that are provided by Scikit-Learn includes clustering, for example, which is part of unsupervised learning. For grouping unlabeled data, such as the k-means method. Cross-validation is another tool provided by Scikit-Learn, which is for estimating the performance of supervised machine learning models on unseen data. Scikit-Learn has a set of data sets built on itself for test data sets, for generating data set with specific properties for investigating model behavior. Also, Scikit-Learn has the dimensionality reduction tool that is part of unsupervised machine learning methods for reducing the number and attributes of our data that it can be used in summarization and visualization, and also feature selection, such as in principal component analysis. The other set of tools included in Scikit-Learn is the ensemble methods, which is for bundling up and combining the predictive models or the supervised machine learning algorithms to make them more efficient and more useful in prediction. Feature extraction is the other tool, which is for defining attributes in image and text data. The other tool is feature selection for identifying meaningful attributes in a set of data from which we can create supervised models. Parameter tuning is the other tool provided by Scikit-Learn, which is for optimizing the behavior of your supervised model, make them to make them more efficient, more productive, and more accurate. Scikit-Learn also have provide manifold learning, which is for summarizing and depicting complex multidimensional data. And also, of course, a set of supervised models, including a vast array to generalized linear models, discriminant analysis, naive Bayes, lazy methods, neural networks, support vector machines, and decision trees, and many more. Before we move on to a complete workshop-like session in which we are going to do all programming and all coding, I want to give you a general picture of our general guideline in the necessary steps that are common to do when you want to apply machine learning in Python. So the first one is, of course, if you want to utilize the power of the libraries that we know for data processing, data manipulation, and data visualization, and other things, you need to import these libraries. The most common libraries that we're going to use in typical machine learning application includes NumPy, Pandas, Matplotlib, and the Scikit-Learn sklearn. So you're all familiar with how to import a library. We're going to import using the command import, then the name of the library, and we can actually give it a nickname such as, I'm going to go with this one, import matplotlib.pyplot as PLT. So PLT is the nickname here, and it makes it easier and simple for later on when we want to use an application or a method from the matplotlib.pyplot. So we don't have to actually write this whole complicated, unnecessary name. We can just use the PLT, its nickname, instead. The next thing that we need to do, we need to work on data. So we need to import or load data. Data needs to be actually numeric. You may be wondering, how about other types of data, such as graph or images or sounds? Even they have to be converted to a numeric data set, because finally this is going to be a computer. It's a binary system. So at the end, it's going to be all converted into 0 and 1. So all data needs to be in numeric and stored as either a NumPy arrays or a SciPy sparse matrix, or other types that are convertible to numeric arrays, such as a Panda data frame. You can have different sources of data. For example, you can have a data set stored in your local storage, or it can be a data set that is online, or actually is a data set that it's within a library. So there are different ways to load or utilize the data. We're going to learn about these three ways. If you have stored your data in a local storage, you can read it with the pandas read underscore CSV command. So you need to put the address of the local storage address and then the name of the file. It has to be a CSV file, and then read it to a Panda dataset here. If your data is within a website, then you can use the address and put it in an URL name, and then use the read underscore CSV to read that the location that your data is stored online. If your data is actually within a library, Scikit-Learn has actually a data set. You can import that data, for example, from a Scikit-Learn import datasets, and then datasets use the command load underscore iris. For example, it's a iris is a dataset. It's a very popular dataset in Scikit-Learn. I'd say even probably the most popular dataset, which is used by machine learning, especially for the educational purposes for the first-time learners. It's very popular. So this is how you can access your data. After reading or importing your data, a common step is pre-processing. The pre-processing step may or may not be necessary. This step actually helps us to prepare the data so that we can get better results out of our model or algorithm. There are several pre-processing actions that could help us to improve the behavior and the results of our modeling and the prediction process. These steps can be including methods such as standardization or normalization or binarization, or even taking care of the missing values in your data, which is actually a common problem, a very common problem when you work with data that is not a standard data. We're going to learn about some of these or most of these later on as we go further into the course. Separating training dataset and testing dataset. In machine learning, the study and construction of algorithms that can learn from data and make prediction on data is a common task. Such algorithms work by making data-driven predictions or decisions through building a model from the input data. The data used to build the final model usually comes from multiple data sets that are going to be from different stages in model application. In particular, three data sets are common. The training data set, the validating data set, and the testing data set. What is the training data set? The training data set is the set of data that is used for tuning parameters of a model, such as weights in some models. The model is trained on the training dataset using supervised learning method. The training dataset often consists of pairs of an input vector or array or a scalar and the corresponding output vector or array or a scalar, which is commonly denoted as the target or label. The model is run with the training dataset and produces a result which is then compared with the target for each input vector in the training dataset. Based on the result of the comparison, the parameters of the model can be adjusted or, as so said, tuned. What is the validation dataset? After the training stage or fitting stage, the fitted model is then used to predict the responses for the observation in a second dataset called the validation dataset. The validation dataset provides an unbiased evaluation of a model fitness or performance on the training dataset while tuning the model's hyperparameters. Hyperparameters are those values set before the learning process begins, such as the number of hidden units in a neural network that we're going to learn later on. Validation datasets can be used for regularization by early stopping. Stop training when the error on the validation dataset increases, as this is actually a sign of overfitting to the training dataset. Overfitting is a condition that in which your model or algorithm is fitted too much or attached too much to your training data set, such that is incapable of making prediction outside of this set of data. The next data set is the testing data set. Testing dataset is a dataset that is used to provide an unbiased evaluation of a final model fit on the training set. When the data in the dataset has never been used or seen by the training session step, for example, in cross-validation, the test dataset is called a holdout dataset. A dataset can be repeatedly split into a training dataset and a validating dataset when you hold out the testing dataset. This is known as a cross-validation that we're going to talk about it later in this course. The test dataset is independent of training dataset but follows the same probability distribution as the training dataset. If a model that is fit to the training dataset also fits well into the test dataset, minimal overfitting has taken place, which is a good thing. A better fitting of the training dataset as opposed to the test dataset usually points to overfitting. So if your model performs well with your training dataset but performs poorly with your testing datasets, that's an indication and a signs of overfitting of your model to your training dataset. Oh no, oh no. Model building and fitting. At this step, you need to choose a model and import it from the Scikit-Learn library. The question of which model you should choose is a very important question, but it doesn't have an easy answer. It takes experience, knowledge of your data and the problem that you're working on, and oftentimes try and error to pick a good model. After you choose a model, you need to import the model and feed it to your data. I'm going to show you a general sketch of a set of lines that usually you have to write to do these steps. So this involves importing your model. For example, from the Scikit-Learn, I'm going to use general names, Scikit-Learn.xyz. This is the set of algorithms or models in a Scikit-Learn. Import a particular model, for example, a model. Let's see an example. For example, from a Scikit-Learn.linear model, this is a set of linear models. Import a particular model, which is linear regression. And next, you need to fit your model into your data. So this is your model, my model name, linear regression, normalize equal to true. This is actually a parameter that we're going to talk about the parameters of each algorithm as we learn about them. And to fit your model into data, you need to use fit xy. Okay, so your your model name, whatever it is, dot fit, and then put in the sample data that you have, which is the training data set X and the label Y. This is going to train and fit your model to your data. Using the model to make prediction. After you have fitted your model to your training data, the training step, it comes to the goal step, which you want to make a prediction using your model. For this reason, we pass the independent variable or data that we have, which is actually the X data, X variable or data, into the model so that the model can make a prediction on the dependent or target variable, which is the Y variable, the labels. For example, we can define a target variable called predict, y predict, and then this is our model. Our model, it has been trained already with the training data set in the training step. To ask it to make a prediction, you have to call just predict dot predict and get it the independent x variable so that it actually makes a prediction on the y variable or y data set and put it in the y predict. Evaluating a model. To judge the performance of a model, we need to use some metrics. There are different metrics available to use. Some of these metrics are actually specific to certain class of models. For example, we can use accuracy score to evaluate the classification type models based on the predicted value that your model has predicted and the real value of the target variable or the label variable. Let's see an example. So the command is accuracy underscore score, and then we give it the real values of the dependent variable, which is y underscore test, and the predicted values predicted by your model, which is y underscore predict. So this is going to ask, this accuracy score is going to give you a judgment based on these two values, how accurate your model has been. For the classification models, we can also use classification report, such as the following. So we have to import from the classification report first. From Scikit-Learn.metrics, import classification report, and then we ask it to predict it, to print it out. Classification report, we give the real values of your labels and the predicted values of your labels. And it's gonna then print out the classification report to a judgment of the performance of your model. There are other models available, some of them specific to certain models. For example, we have confusion metrics, we have the mean absolute error, mean squared error, we have R2 score, and many more that we're gonna talk about it later on in the course. Some of these metrics that I mentioned, you are already familiar with them based on the regression topics that you have learned in, for example, in your statistics class. For example, the mean absolute error or MAE or deviation is a metric that you already know from statistics. So MAE is equal to the summation of the deviation from your real values and the predicted values, and then finding the average over them. By the way, this is, if you remember, the deviation of your predicted values from your real value is the error in your model. The other one is the mean squared error or MSE. MSE, instead of finding the absolute value, it finds the square of the error that you have and then find the average of that. Also, you might remember the R score. The R squared. The R squared is 1 minus the summation of the deviation of your predicted value from your real value squared divided by the deviation of your average value of y values from the each y value squared. So this value is going to give you the R squared.